Welcome, dynamics students. This is the first of our mini lectures on rigid body planar motion using work energy considerations. So, advantages of work energy versus straight up kinematics. Typically less kinematics calculations involved. So typically when we were looking at particle motion, we would, if we had, say, a particle and it's undergoing some kind of motion, we can look at, of course, its motion, tangent, get acceleration, tangent, and normal on a path. We can look at forces acting on the body, maybe in the x and y direction of a coordinate system. And we can draw a free body diagram, and we can solve for the sum of the forces in either the I hat or j hat direction as equaling the mass of the particle times the acceleration in the x or y. With a body that had some center of mass somewhere, kind of put it right in the middle, we could do the same thing. We could add up all of the forces and the moments. Use our symbol for moments. And we could do the same thing. We could say the sum of the forces on that rigid body in each orthogonal direction, I hat, j hat, and we'll draw a little. And we're really only having to worry about I hat and j hat because we're restricting ourselves to planar motion is going to be equal to the mass of that body times the acceleration of the center of mass in the x or y direction. From that, we can write expressions for acceleration maybe in a tangent normal system. We can relate the acceleration to maybe the rigid body's velocity or velocity squared and its angular acceleration. So that's where we can punt down to our kinematics. Maybe we can invoke things like rolling. We can relate the center of mass to the point of invariant or zero instantaneous velocity. We can look at rolling on a curved surface. We can look at all kinds of twisting, rotation about a fixed axis. Maybe all kinds of stuff that could be happening in terms of the kinematics of that motion. And all of that will be rolled into acceleration expressions. In the case of rotation about that center of mass, we capture that by saying the sum of the moments about the center of mass is equal to the moment of inertia of that rigid body about the center, taken about the center of mass times the body's angular acceleration. So basically ma versus I alpha are kind of our one-to-ones. And of course this entire expression we didn't have with particle kinematics because a particle can't sustain a moment. And when we look at a whole rigid body, we have to look at the fact that we can sustain a moment even though the distance between all the particles in the body stays the same throughout the motion. That's the definition of rigid body. They can still rotate about any point. So this is the difference. So again, when we're applying kinematics and kinetics, we look to sum the forces, set them equal to mass times the acceleration of the center of mass in our two orthogonal directions, and then we sum the moments, and we set those equal to the moment of inertia, typically about looking at points about the center of mass. This works, and we've done problems like that. But the problem with this approach quite often is the kinematics. We can get some real complicated equations of motion applying rolling. We may have to apply some crazy curvilinear motion, which we can do, but there can be an awful lot of math that results from that. So when we're doing kinetics, the path matters. The path we take is important for understanding forces and acceleration, especially if we're working with friction. So the distance we move when we have friction acting is very, very important. It would be a lot easier in a lot of cases if we only had to consider the starting condition and the ending condition. So if we knew we got a body moving along some path, whatever, and it's subject to some forces, it's got a moment, it's got a force here or there, whatever, and it ends up in some other configuration. And it would be nice if we only cared about the initial and the final states. It would be really nice if we could find some expression for what happened mechanically to this, forces, moments, such that we could get an initial and final position, angular orientation versus some coordinate axes, acceleration, etc., just based on the initial versus final state. If we knew something about what happened here and here, we could back infer everything else without having to maybe integrate along an entire path or consider the exact nature of that motion, all of the complicated kinematics, tan normal along some path that's time dependent, and parametric equations, which we can do, but that's a lot of work. So if we could just do two states, what's going on at the beginning and what's going on at the end, and from that and for everything we might want to know about the mechanics of motion, that would make our lives way easier. That is the essence of work energy. And we saw this basically with particle motion. We applied it, gravitational work, spring work, work of friction if we didn't have conservative forces, in which case all we needed to know was the distance. We didn't need to know the exact path necessarily if our friction force was constant. So that was the one path-dependent element we had to wrangle with. Now we're going to extrapolate this to rigid bodies undergoing planar motion. Just like for kinetics, which means effectively we're going to consider the work of gravity acting on the center of mass, the work of a spring force, a linear spring, acting on the center of mass, and we're going to look at kinetic energy of the center of mass. And here's the one new one. We're going to look at kinetic energy rotational. And that's kind of the new player that we're going to see as we go from particle motion to rigid body planar motion. Because we have a rigid body, we will also, when we look at work of forces, in addition to having the sum of the forces being a force resultant doing work, by acting along some path, we're also going to look at the work done by a moment, because rigid bodies can sustain moments, so we're going to look at the resultant moment doing work around an angle. So how much does that moment rotate the body? If we've got a net moment, say, sticking out of the page, that's our resultant moment. Let's draw that double arrow a little bit better there. We'll just take a moment to draw the moment arrow. You knew that was coming. So that indicates rotation in this direction. Basically, if that moment force, which could be caused by forces acting at some distance from this point, the body is going to rotate through some angle due to the action of that moment, probably a couple moment in this case. That will also represent work, and if the work is being done on the body, then its energy state goes up. Just like the work of gravity, if it's acting on the body, we go to a higher elevation, or if we're moving something through any kind of potential gradient, if we move a charge through an electric field, same thing. But in terms of changes that we're going to see with rigid bodies in planar motion with work energy, the big differences from what we've seen with particles are going to be our rotation, and then the need to look at the work done by a resultant moment. Otherwise, we can look at the changes in position versus a spring force or a gravitational force of the center of mass, and we can also look at the kinetic energy of the center of mass of a rigid body. We just need to remember that kinetic energy due to the 1/2 mv center of mass squared is not the only kinetic energy. There's also the rotational kinetic energy, which is our 1/2 I center of mass times omega squared. Notice the similarities. Just like our Newton's second law, our kinetic energy of rotation, it looks pretty similar. So our moment of inertia about the center of mass is basically taking the place of mass for our linear kinetic energy, and then instead of the velocity of center of mass, we have the actual angular velocity of the entire rigid body. Okay, so armed with that little intro, I'm going to dive into some example problems. These are all drawn from the Hibbler Dynamics textbook, 14th edition, and these are all coming out of chapter 18, which is the work energy for rigid bodies in planar motion. So this is kind of our analog to I can't remember the chapter for planar motion. So we're going to start with something that's pretty simple. We have a spoked wheel. And we've got some mass out here kind of in a ring. And then we have two rods that intersect inside. And I'm drawing everything pretty thick. But we can assume that this ring is fairly thin, that it doesn't have a substantial thickness. And we have and the center point is point O. And we have an applied moment. And it is equal to the moment as a function of theta, the angle that it's turning. So m is a function of theta equals 2 theta, and that is in units of Newton meters. So we're not going to have the units carried in this coefficient. If we were being real proper about it, we would carry those units in the coefficient. So when we integrate, things would change. Of course, theta is unitless, so it probably wouldn't matter. But basically, the more it rotates, the more moment is applied. And in this case, we're told that there's a little torsional spring here, like in a watch. So basically, rather than a linear spring, which is going to have a force equal to negative k delta L, a torsional spring is going to have a moment that's equal to some k, and it's going to be pulling in the other direction, proportional to delta theta. So the bigger the angle that you twist it, the greater the moment that it's going to exert. And by the way, these kind of torsional springs, in addition to being in old-fashioned mechanical wristwatches, they're key to the action of a mechanical viscometer. So anyone who's doing fluid rheological measurements, you're going to be relying on a torsional spring. So just like in this problem. Okay, so we know what's creating this moment, that torsional spring. And we are asked to find out at what the angular velocity is at, I believe, a certain angle or time. It's a certain angle. So we're asked, what is omega at 2 revolutions? So we have the moment acting on it, and it's accelerating this wheel rotationally. It starts at rest, I believe. Just making sure what our initial state is. And released, its determined maximum angular velocity if it is rotated 2 revolutions, then released from rest. Okay, so what's happening is we're going to wind it up. And we're told that the moment that we're going to exert is dependent on how much we wind it. So we're going to wind it 2 revolutions. 2 revolutions is 2 times 2 pi equals 4 pi. So we're going to wind it up. So we're going to allow that spring to do some work as we wind it up through those revolutions. Then we're going to let it go, and we're going to say, okay, after it comes back, the spring energy is released, what's its angular velocity? We could, find an acceleration and integrate with time once using moment. But we can also look at our initial state and our final state and make it even easier, because we only care about this initial state when it's all wound up, and then 4 pi later. So we can use work energy in this case, and we can use the work done by the spring. So we can say our total energy state initially, it's at rest, so kinetic energy equals 0, and we'll call it our work of torsion, our spring, which is going to be equal to kind of a spring energy. We'll call it U spring, because it's that spring that's causing it, that's giving us the moment, is equal to, this is a fairly easy integral, but the work that's done on the spring by turning it is going to be that moment expression times d theta, from theta equals 0 to theta equals 4 pi. So that equals the integral of theta squared, because remember m was 2 theta, so if we take the first derivative of theta squared, we get 2 theta. So this is going to be evaluated from 0 to 4 pi, and that gives us 16 pi squared in Newton meters. So it's not moving, but it has 16 pi Newton meters of spring energy in its initial state. We're going to let it go. It's not going to do any work against gravity. It's got a frictionless bearing. There's not going to be any work of friction done. So the only thing that's going to happen, final state, we're going to take all of that spring energy and convert it to kinetic energy. So we're going to say U spring equals 0. Kinetic energy equals, we don't know. But we do know kinetic energy is related to our angular velocity, which is something we wanted to know. So basically we can think of this as a conservation of energy. We're going to take all the energy that is stored in that spring, which was created by the work of torsion against this moment, and we're going to dump it into kinetic energy. So the question remains, how do we write an expression that relates? We know how much kinetic energy we have, by the way. We know how much that is. That's the 16 pi squared. So all we have to do is say, okay, how does this increase in kinetic energy change my rotational velocity? So really all I need is an expression for kinetic energy in terms of rotational velocity. I know what my kinetic energy is. It's all of the spring energy. Spring energy didn't go anywhere else. So I need an expression for kinetic energy of the wheel. Well, the wheel is rotating. The center of the mass of the wheel at O, it isn't moving anywhere. I could do a little coordinate system here. IJ. It ain't moving. It's stationary. We got a fixed pivot. So the kinetic energy of the wheel is only due to its rotation. We could say velocity of the center of mass equals 0. Okay. So that means we are looking for 1/2 I center of mass times omega squared. And hey, here's our omega that we wanted to solve for. So really all we need is I center of mass, because we know this is all equal to our 16 pi squared Newton meters. So we can use our method of composite moments of inertia, and we can say that our IC total equals I ring about its center plus 2 times I rod about its center. So basically we have three things that we're going to start accelerating. We have the ring, and we've got one rod, and we've got the other rod, and the two rods are the same. So we can, in the interest of saving time and pain, we can use, since we're doing everything about the center of mass, we don't even need to use the method of composite, we don't need to use. We are using the method of composite parts. We don't need to use the parallel axis theorem. So we can refer to our the handy-dandy formulas in the back of our textbook, or we can go to a handbook and look for the moment of inertia of a thin ring about its center. So this will be, you'll find it under something like IZZ ring, sticking straight up through the center, and that's equal to mr squared. And so that's the radius of the ring. And if we look at the problem, we're told that that radius is, I believe, 0.5 meters. I'll just draw it on there. And we can look at the average radius because it's thin. And we're told that it weighs, the ring weighs 5 kilos. So IZZ ring is going to equal 5 kilograms times 0.5 meters squared. Now we've got our rod. So we know that the moment of inertia of a rod about its center is going to be 1/12 times the mass of the rod times the length of the rod squared. We were told in the problem that the mass of each rod was 2 kilograms, and the length of each rod is just the radius of that wheel times 2. So we're going to have 1 meter there, and we're going to square it. So, and then we're going to have 2 of these. So if we add all those together, 5 kilograms times 0.5 meters squared, and then 2 of 1/12 times 2 kilograms times 1 meter squared, we get a moment of inertia about the center of the total composite part is going to be equal to, checking my notes here, I believe it ends up being 1.5383 kilogram meters squared, which is the proper unit. And I'm going to do a quick calculation, check myself, make sure I'm reading my notes right. Never hurts to do that. 5 enter, 0.5 squared times, then we've got 2 enter, 12 divide, 2 times plus 1.583. There we go. I was correct. So we can plug this in right up here and basically just solve for omega, which we would do 16, enter, 3.14159 squared times, swap, divide, and do not forget the 1/2, and we end up with, we'll run through that again. So omega is going to equal 16, I'm running through the calcs live, 149 squared times 157.88 is Newton meters, and we 2 times, divide by IC, 1.583 divide, squared, and we got, so I'm going to write this out, 2 times 16 pi squared divided by IC, square root, equals 14.1, give or take, radians per second. So basically just solving for omega. And the easiest thing to forget when we're doing this is the 1/2. Especially if you're used to kinetics problems where you have your moment of inertia times alpha. Here you need to think this is kinetic energy, so there's always going to be a 1/2, and this is going to be a squared term. So real simple case, we had a torsional work, so a moment was exerted through an angle, which resulted in accumulation of spring energy, which was all transferred into kinetic energy. And that kinetic energy, because the velocity of our center of mass at the point of interest was 0, was all rotational. So we could use our expression for kinetic energy of rotation of a rigid body about its center of mass equal to the entire accumulated spring energy to find our final rotational velocity. So that's it for this one problem, and you can stay tuned for a second problem. Okay, welcome back, dynamics students. This is the second of our work energy of rigid bodies in planar motion problems. The previous problem that we just finished, I'm pausing and doing multiple problems here in a single recording. That was just for reference. The previous problem, the wheel with the spokes, was problem 18.3 from the Hibbler 14th edition, chapter 18 dynamics book. And now we are working Hibbler 1814. So if you want to reference that in the textbook. So in this case, we're given a single rod. It's uniform. So the center of mass is at the center of the volume. So 1.5 meters down from where it's hanging. It's hanging from a pin, a frictionless pin that allows the rod to spin around 360. It's being pushed by a 150 Newton force that we're told always remains perpendicular to the rod's direction. So when the rod's over here, we've still got the force at right angles. So given that we've always got a perpendicular orientation of the force with respect to the radius from our pivot point to the end of the rod, we can think of this 150 newtons as a fixed moment. We're always exerting 150 newtons times 3 meters. So basically we're always exerting 450 Newton meters of moment. Now, as we push the rod up, that force is going to result in an increase in kinetic energy and an increase in gravitational potential energy. So we're doing work against gravity, and we're also contributing to a rotational acceleration. In this case, the center of mass is moving. It is moving to a new position. So we're going to have expressions that include the rotational kinetic energy, and we're going to have a change of position of the center of mass. And because we don't have a zero, we're not rotating about the center of mass itself, the velocity of the center of mass is not equal to zero. So when we look at kinetic energy, we're going to have to look at the kinetic energy of the mass center moving, as well as rotational components, or look at a way to relate them together. So what we're asked in this question is, and it's drawn a little oddly in the book, you wouldn't think that it can rotate 150 degrees, so I've drawn it as being attached to the rod attached to a free pin here to make it a little bit easier to look at. But we're told that this 150 Newton force pushes the rod such that it flips all the way up 180 degrees. So now it's vertically oriented but completely opposite, 180 degrees, or pi is our delta theta if it started hanging downwards. And we are told that I believe we're told that it started at rest. It's suspended at rest. We apply our 150 Newton force. We keep applying it through the entire motion. It maintains its perpendicular orientation to the rod. And we're asked, what's the angular velocity when the rod is up at this point? So we could, if we wanted to, maybe look at the force accelerating the center of mass. We know that a component of it is going to lift the center of mass. We could get an alpha. We do have a moment, and then we could look at the portion of that force that was tangential, subtract the tangential component of the force of gravity. Yeah, we could do this problem with kinetics, but it's a whole lot easier to do with work energy. So we can basically say, what is the total energy initial so kinetic energy initial is 0. We're going to say that this reference elevation for the center of mass is 0. We'll call it h equals 0. It's basically like sea level in this problem. So we'll call it U gravity equals 0. There's no springs. So basically we can say we're starting at a 0 energy state. We do work. Work done by the applied force. And we can look at this as the work of a moment, basically. So we can say it's akin to the work of a spring. So we can say the increase of energy. Well, let's not look at that as energy. That's not the easiest way of looking. Let's just say the work of the force. We're going to rotate from 0 to pi all the way through here. And we're applying a constant 450 Newton meters of moment because we're retaining this force orientation perpendicular to the rod, d theta. So that's going to equal about 14 Newton meters. Okay, so we've added energy effectively. We've done work on the rod. So we have 1414 Newton meters or joules added to the system. This is going to go into an increase in the gravitational potential energy or work we're gonna have work against gravity. We're going to lift that center of mass from its reference position to h equals 3 meters. So we have 1.5 plus 1.5 is 3 meters. So that's going to basically be mgh. So we'll have 10 kilograms times g, 9.81 meters per second squared, times 3 meters. So that's how much we're going to lift it. And that comes out to 294.3 Newton meters. And we're also going to increase its kinetic energy. And that's where we're going to get an expression for the velocity that was wanted. So somebody wanted to know, determine the angular velocity. So we wanted to know at theta equals pi. Okay. So we can get a total kinetic energy by just subtracting this expression from that and know how much we have. So if we do that, we find that our increase in kinetic energy is equal to, we'll call it about 1120 Newton meters. It's 1119.7, but we're pretty darn close. So we can look at it two ways. We can either look at rotation about the center of mass, or we can look at basically rotation of the entire body about the end of the rod. So we can look at this in terms of a 1/2 I rod end times omega squared. So in this case, we do have, we do have the center of mass moving. We've moved it upwards. We can't use the moment of inertia about the center, where we're actually rotating about this endpoint. And so we're basically applying the parallel axis theorem, and that captures not just the rotation of the body about its center of mass, but the movement of the center of mass as well. So we're basically looking at that curvilinear motion of the center of mass plus the rotation of the body about its own center of mass in one, but just applying the parallel axis theorem and using this expression for I rod at the end. So the moment of inertia of a slender rod about its end, we can look that up in a handbook as well and find that it's 1/3 times the mass of the rod times the length of the rod squared. Now compare that to 1/12 if we're rotating about its center of mass. So that is a big change, that additional mass out from the, at a longer distance from the pivot point. And so in this case, we have a mass of 10 kilograms. We've got to use the entire length of the rod, which is 3 meters. And so we get an I rod about its end equal to 30 kilogram meters squared. Now I'm going to switch colors. We can use that in this formula. We know that the total kinetic energy available was 1120 Newton meters. That equals 1/2 times 30 kilogram meters squared times omega squared. We solve for omega and we get about 8.64 radians per second. So compared to our spoked wheel problem, this is very similar. Again, I'll write down the reference. This is Hibbler, 1814. We had zero energy state to start with. We did some work. We did that work with a moment working through an angle as opposed to maybe a force working through a distance. Same deal. That work done on the body went into an increase in gravitational potential energy, which we could capture with the movement of the center of mass. We're not having to worry about rotation in that case. And then an increase in kinetic energy, which we were able to capture 100% rotationally by using the parallel axis theorem and noting that we were rotating about one end. So we didn't have to break up the kinetic energy into translation of the center of mass plus rotation about the center. We could have, but it was much easier to just use the parallel axis theorem and get an expression for the moment of inertia about the actual pivot point about which the rotation was occurring. So very simple compared to having to write an expression for the component of the force that of both gravitational and applied forces that were in the tangential direction continuously through the entire motion, which is what we would have had to do to solve this with a kinetics approach. Basically just two equations. So that is it for this problem. Hang on just a second. I'm going to pause and then queue up with a third problem for the day. Okay, welcome back, dynamics students. This is our third and final work energy of rigid bodies problem that we'll include in this recording today. And this is taken from the Hibbeler 14th edition dynamics text, problem 1829. So in this problem we have a hill, and it's a hemispherical hill, or maybe a cylindrical hill. And we have a sphere, maybe a big marble, that'd be a pretty big marble. It's a half a foot radius, and it starts up here at the top of the hill, and it starts at rest, so we can immediately write kinetic energy initial equals 0. And the hill is, maybe it's a mound in the garden. It's 10 feet in diameter. So we're starting with with some elevation, and then the sphere rolls down the hill. We're told it's rolling. And that's very important. It doesn't slip. It's rolling. Now let's take a look at what does rolling tell us right here. Immediately, when we hear the word rolling, we have a relationship, especially when we're talking velocity. And this is particularly useful when we're applying work energy. Remember, if you're rolling, you've got this I'm going to draw it in red because it's invariant. Velocity is stopped. We've got this point, this invariant point, I call it, this point of instantaneous zero velocity right at the contact point. And then we've got our radius. So we have a relationship, because this is 0, we can apply our rigid body planar motion, and we can say the velocity at point C is equal to the velocity down there at point I plus omega, the rotational velocity of the body, which is going to be in the k-hat direction. We got our plane, we're in planar motion here, cross r I to C. So for a body rolling along, that means basically if we're rotating this way and our I to C, we're rotating, this is negative, I to C is positive, so we're going to have basically V sub C is going to be in the positive I hat direction, and it's going to be equal to omega times the radius of in this case, the radius of the sphere, or whatever body, average radius of the body, or the radius at that instant. If it's round, it's the same radius all the time. And it's going to be in the I hat direction. We don't have to worry about the surface that it's rolling on not being flat. If we were looking at the acceleration of that sphere rolling, we'd have to look at creating an expression for acceleration of the center of mass that took into account the fact that it's a curved surface, and it would be different than it is for a flat surface. But velocity doesn't matter. That's going to be the case curved or flat. At that one point in time, this relationship between the point of instantaneous zero velocity, which is the contact point, if we are truly rolling, which we are in this case, it's always going to have this relationship. So we now have a nice relationship between omega and the velocity of the center of mass of the body. So if we know one, we can relate to the other. So we kind of have an equation over here. We'll call it equation number one, relating those two things, because we might need to know one or the other. And in fact, we are asked to determine the speed of the sphere's center of mass at the time when this omega, or this angle here, is 45 degrees. Okay, speed of the center of mass means v tangential, and in fact velocity is always tangential. So we're looking at basically v sub c there. Why is it going to be important? Why is it going to be important to be able to relate v sub c to omega? Because that ball isn't sliding. It isn't a little particle that's sliding along a curvilinear path. It's rolling. So it's rotating about its center of mass, and that center of mass is itself moving. So we've got two components of kinetic energy that we're going to end up acquiring. So what is imparting that kinetic energy? Second law of thermodynamics says we're not going to create energy. So how did we get that kinetic energy? Well, gravity did some work. So when the ball has rolled from the top to a position where theta equals 45 degrees, we went from a height initial was 10 feet. So we can say that the work of gravity on the sphere is equal to 10 feet minus 10 feet cosine 45 degrees times the weight of the sphere, which is 10 pounds. So we can say that let's see if we got an expression for that, and that ended up being 29.28 foot-pounds. Okay, so that's how much total kinetic energy that we can acquire. We're no frictional losses. We're not increasing elastic energy somehow. We're not compressing any springs or deforming any bodies. We're a rigid body. So this is all going to go into change in kinetic energy. And there's going to be two components of that. We're going to have a change in kinetic energy of the center mass plus we're going to start rotating it. Okay. Well, we've got an easy expression for this. 1/2 mv center of mass squared. And in this case, the mass is going to be, let's see if we have it in slugs here. 10 pounds is equal to 0.31 slugs. So we have 1/2. And the velocity of the center of mass, because we are rolling, we can relate that to omega, which is pretty nice. So we can say we've got 0.5 feet times omega all squared. Then we've got to add our rotational kinetic energy. We're not a particle sliding. So, of course, that's going to be 1/2 I sphere. So it's a sphere, and it's rotating about its center of mass, times omega squared, same omega. So we have only one unknown. We can look up in a handbook the moment of inertia of a sphere rotating around itself, and we find that that is 2/5. Again, this is in the back jacket of Hibbler. M times the radius squared. So that's going to be 0.5 feet. There's our 0.31 slugs. So literally it's the same term as we have over here. So we have 1/2 times 2/5 times 0.31 slugs times 0.5. I'm going to erase this to give myself a little room. 0.5 feet times omega all squared. And that is equal to the energy input from gravity doing work on that sphere, 29.28 foot-pounds. So all we have to do is solve for omega. We have one equation and one unknown. And when we solve for that, we'll change colors. We end up with an expression for omega of 23.2 radians per second. And then we kind of go backwards. Our velocity of our center of mass equals r omega. So we're going to get a velocity of the center of mass when theta is 45 is going to be about 11.6 feet per second. So depending on exactly what value used for gravity, this can change a little bit, but it's between 11.5 and 12, and I ended up calculating about 11.6. So this is, in case you haven't noticed, I've started using, this is not the section in Hibbler for conservation of energy, but I've started using that theory. We get an initial state, we do some work, or work's done on it, we gain or lose energy, and then we look at the change in state. And in all cases, what has been of interest was the change in kinetic energy. Some form of it. This time we were looking for a difference in the velocity of the center of mass, and in the previous two questions we were looking at the difference in rotational velocity. But in all cases we used something that we knew about the change in energy state or work due to a known force, a spring force, change in spring energy, change in gravitational energy, to infer a change in kinetic energy. And this was really the first time we had to use anything harkening back to our kinetics, or excuse me, our kinematics, just to relate the two components of our kinetic energy that we were going to acquire and get that last equation that we needed to solve for what we needed to know. But we certainly didn't have to go through as much intricacy of calculation as we would have if we had been representing gravity as a force that was resulting in an A tangential of the center of mass and an alpha about the center of mass. We could have done that, obviously, and used our acceleration equations for a rolling body on a curved surface. We have derived that in our rigid body kinematics, but this was much easier to do because we only had to consider initial and final state. So that is it for today's demo problems, and a little bit of intro to how convenient work energy is for rigid bodies as well as for particles. And we're done now, and in our next lecture having to do with work energy for rigid bodies and planar motion, we'll do more examples that rely on conservation of energy directly. Starting energy state, final energy state, solve for what we need to know. And in those cases, we may be looking at knowledge of kinetic energy in final and ending states, and then use that to back calculate some change in potential, gravitational, how far does the spring compress, etc. So we can go either way, they're interchangeable. So stay tuned for that in a future lecture.